Okay, so we are now going to push into section 6.7 where we will see the connection between your savings account balance and exponential functions. Okay. So first thing that we're going to do is determine the future value of a lump sum of money. So the ideal is this, is that we make some deposit into a savings account and we sit back and watch it grow. How does it grow? It grows because of compound interest, right? So at the end of each period, whether it's a week, month, year, whatever, the bank is going to take a look at that balance and then assess a certain percentage of it, either the APR or a fraction of the APR, and that percentage of your balance will then be added to your balance, creating a higher balance, and then that'll create even more interest next time, and then add it to your balance, and so forth. So you have this compounding effect. And what we're going to do is we're going to look at determining the future value, as in the future balance of that bank account. When you put in a chunk of money and you don't do anything to it, there's no fees, there's no withdrawals, no money added to it. You're just putting it in there and letting nature take its course. Now, you probably learned a long time back that there's two types of interest. There's simple interest and there's compound interest. Simple interest is where you just take the principal, which is that bulk amount, that principal, that lump sum. That's what P is, the principal. And you take the interest rate, which is a decimal, or you convert it to a decimal. So if it's 3%, you put in 0.03 here. But think about it, though. Interest rates are expressed as a percent per unit of time. For example, 3% per year. So your interest rate R has to have the same units of time as T, because T right here is going to be the number of units of time. So if you have an interest rate of 3% per year, then T has to be in terms of years. Or if it's 3% per month, then T has to be expressed as the number of months that have passed. So if you are in the statement of a problem told years, but your interest rate is in terms of months, then you have to convert your years into months by, multiplying by 12, for example. I'm sure that you know how to do conversions of time. So adjust accordingly. But I is the simple interest. It's just going to be a certain dollar amount based on the principal, the interest, and the time. I is equal to PRT, a very famous equation. All right. Now, the typical term for interest is going to be annually, which means once per year. But you could have semi-annual term, which means twice a year, or quarterly, which is 4 times a year. Monthly, 12 times per year, is when you might have your term come up, your period, what they call a period. Or daily. We'll not mess with any leap years, okay? So just assume 365 days. So if you have daily compounding or a daily period, that means that there's 365 of them per year. So we're going to try to make that connection between simple interest and compound interest here. Now we have a credit union that pays interest of 4% per annum. What does per annum mean? That's another way of saying annually, right? So 3%, 4% annually. So 4% APR, in other words, think about this as 4% APR. With quarterly compounding. So it says per annum compounded quarterly. Please don't get those mixed up. They mean 4% APR with quarterly compounding. That means that at the end of each quarter, so for example, if you, basically a quarter is going to be what? March 31st is the end of the first quarter, June 30th is the end of the second quarter, and so forth. At the end of each quarter, the bank is going to look at your balance and then take your APR divided by 4, which in this case is 4% divided by 4, which is 1%. Take 1% of your balance and add that to your current balance on your certain savings plan, lump sum, essentially. If $2,000 is deposited in such a plan, so $2,000 is your principal here, and the interest is left to accumulate, how much is in the account after 1 year? So how compound interest works is that simple interest is applied once per period. Okay. So here's simple interest for the first quarter, where you had the $2,000 starting balance, P, right? And the interest rate was 0.04 per year, and times the time, right? The time was 1/4 of a year. Make sure that those times periods match up. This is I is equal to principal times the interest times the time. And that interest works out to be $20. What's going to happen to that $20? It gets added into your balance. So there's your new principal to start off your second quarter. And then we will do simple interest again at the end of that second quarter. But this time the new principal is $2,020. But with the same R and the same T. All right, I'm going to go through this. So you add $20.20, which, by the way, is a little bit more than what was added last time because you had a bigger balance. So you add 2020 to your new principal, or to the existing principal to make this new principal of 2040.20, right? And then, so at the end of the third quarter, simple interest again on that principal for that third quarter. Now your interest awarded to you is 2040. And that gets added. Don't worry, I'll give you a minute to look at this when I'm done. And your new principal for the fourth quarter is now 2060.60. Now, what's going to happen on December 31st? Or the last working day of the year before the new year? Interest is going to get applied to that principal for the fourth quarter, right? Again, it's simple interest each period. 2061. And that gets added to your existing principal. All right, so I'm going to give you a minute to write this down if you want. So I'm going to pause my recording. All right, moving along here. Now, let's see what it is that we did for each of those periods in terms of applying interest. We did simple interest, right? Principal times interest rate times the time. But what was the time? The time was really just a fraction of a year. And because the interest rate for these calculations is going to be an APR, annual percentage rate, as in a percent per year. So the 1 over n represents a fraction of a year. So, depends, of course, on what or how many compounding periods there are per year. If you have quarterly compounding, then n, which, by the way, represents the number of compounding periods per year, n would be 4 for that example. So you would have 1/4 there. Or if you had monthly compounding, this would be, this 1 over n would be 1/12. Or if you had daily compounding, that would be 3/65, whatever. Okay, so just understand that. So now we can go back and try to develop a more general sort of formula for dealing with these compound interest situations. So this time I'm not going to tell you how many times per year we're going to compound. Let's just assume it's generically n number of compounding periods per year. Could be 4, could be 6, could be 1, could be 12 or whatever. And at the end of the first period, we take the existing principal and add the interest, right? But the interest I is equal to, PRT, but T was 1 over N. So you have P plus P times R over N. Now, using a little bit of algebra here, we can simplify this, and write this as P times the quantity of 1 plus R over N. So if you tell me what the principal is and what the interest rate R is and the number of compounding periods per year, I could tell you exactly what your balance is going to be at the end of the first period. Okay? So far so good, everybody? Okay? Moving along here. Now, after 2 periods, we could treat, by the way, this right here as the principal for our second period. And so, therefore, this right here is our principal, and then this right here, where we multiply by R over N, is going to be our interest. This right here, remember, is the principal times the interest times the 1 over N, right? The fraction of the year. So this is principal plus interest. And now you algebraically manipulate it. I know it looks a little bit confusing, but just understand that this first part is the principal, and this is the interest for the second period.
This is just breaking down what we just did.
Yeah, but this is now for the second period. This is a repeat of what we did up here, except instead of P, you have P times 1 plus R over N. Because remember, at the end of each period, that principal, you add interest to it to make a new principal. So if you look at this expression right here now, you can factor out the 1 plus R over N. and factor out the p, and what you're left with is another 1 plus r over n. So that means you got two factors of 1 plus r over n. So you could write this as p times 1 plus r over n quantity squared. So if you tell me what the beginning principal was, and what the interest rate is, and what the number of compounding periods is, I could tell you what your exact balance is going to be at the end of the second period. And by the way, it's really the same calculation as the first one, except there's a square, aka second power, second period. So what do you think it's going to look like for the end of the third period? Is it going to be a repeat of the same, right? Except more complicated, but essentially the same. And what you end up with is really the same thing with the third power. And ... So you tell me the principal, the interest rate, the number of compoundings per year, and the number of periods that have passed. And the number of periods that have passed will be the exponent. And I can calculate what your ending balance is going to be using this formula. Okay? So far, so good? So here's actually the famous compound interest formula where you have your account balance A is going to be the beginning principal P. That's that lump sum of money that you put in, that you initially invest. And then you have your interest rate R. That's going to be an APR, annual percentage rate, divided by the number of compounding per year, which again depends, of course, on what. If you have annual compounding, then it would be 1. If you have quarterly, then it would be 4. If you have semi-annual, then it would be 2. If you have monthly compounding, which is actually most typical for us, how often do your bank statements come? How often do your credit card statements come? Your mortgage statements, etc. Usually on a monthly basis. So for a lot of our day-to-day typical sort of calculations, n would be 12. If you have daily compounding, which is a lot more rare, then that would be 365. There are a lot of big financial organizations that borrow money from each other overnight on the order of millions or billions of dollars. And banks charge on an hourly basis instead of on a monthly basis. So you could have, hourly compounding. It's possible. And then T, what do you suppose T stands for? So n times T will be the exponent that tells you the number of compounding periods that have passed, which is going to be n, which is the number of compoundings per year, times T years. So if you have monthly compounding and 3 years have passed, then that exponent will be 36, right? Any questions so far about the compound interest formula? We developed it because, it's important to see where a formula comes from other than just being told, here's your formula, have a good day, right? Yeah. Have you ever been given those formulas and you're like, where did that come from? Maybe, maybe not. I mean, it's always good to know where these things come from. It's kind of satisfying, actually, to be able to develop them from scratch. So here it is. There's the famous compound interest formula. Compound interest formula. Okay? So make sure that you imprint this on your cerebellum because this is going to be very useful for you. Okay, so This is really nothing more than a formula, though. Formula basically is an equation where you are relating two or more unknown quantities. A is the future balance, P is the principal, R is the interest rate, N is the number of compounding periods, and T is the number of years that have passed. So you have 1, 2, 3, 4, 5 unknowns there. All you need is 4, and then you can solve for the fifth one using some algebra. By the way, you could have your graphing calculator do some of the heavy lifting for you. You could just plug in, X as your number of years that have passed, for example, by putting in an equation like this or a function like this in your equation editor, and then plug in whatever interest rate that you want, and then you could see how the balance increases pretty rapidly, as in like exponential growth. So if you start off with, say $1, then you could see over a period of several years how the balance increases. This is actually 30 years that are passing here. 30 years. And of course, the longer that you have your money in there, the bigger the balance, and the more rapidly your balance is going to increase. Okay. But this is the sort of exercise for you to do, though, on your own. In fact, you'll have a chance to do this in your homework in my math lab. I'm quite sure. All right. But basically what this problem is telling you is that, the higher your interest rate, the more rapidly that your balance is going to increase. That's kind of the gist of the problem, though. But you'll have the chance to explore that when you do your homework. All right, so we're going to do this problem where we are going to compare investments using different compounding periods. With one investment, we're going to have annual compounding, and the other one we're going to do semi-annual. Another one we're going to do quarterly, we're going to do monthly, and then daily. So we're going to invest $1,000, and we're going to check our balance at the end of the one calendar year. Now, when you have annual compounding and T is equal to 1, as in 1 year has passed, then this is just the calculation for your account balance, where P is the $1,000 and R is the 10%, which you express as a decimal, 0.1. So in other words, 1.1 times $1,000 is $1,100. So if you have annual compounding with 10% APR at the end of 1 year with an initial investment of $1,000, your ending balance will be $1,100. Do you suspect that if you have semi-annual compounding that you'll have a slightly higher balance? Well, let's take a look here. This is what it looks like if you have semi-annual compounding. Remember the compound interest formula. The principal is still going to be the same, 1,000. But this time n is 2. So that's why you have the divisor of 2 and the exponent of 2. And then you plug in the 0.10 for R and the $1,000 for P. And you end up with $1,102.50. A little bit higher of a balance compared to the annual compounding. Okay. So based on what you see here, do you have reason to believe that quarterly compound is going to do even better for us? What do you think? Give us a little bit more money? Well, here's our quarterly compounding. So n changes from 2 to 4. Other than that, it's the same calculation. And notice, by the way, we get a little bit more of a balance. So as you can see here, at least anecdotally, the more often we compound, the better the return on our investment, the higher the balance. So with the monthly compounding, daily compounding, getting a little bit better return at each step. And the natural question is, by the way, what is the limit? I mean, how often can we go beyond just daily? Well, you could do hourly compounding, you could do by the minute compounding, by the second compounding. In fact, you can essentially let n become infinitely large, which means that your compounding period itself becomes infinitely small. So we will see shortly of what the compound interest formula looks like when you have an infinite number of compounding periods per year, in which case we have what they call continuous compounding. All right, can I go forward from here, or are you still writing? All right, moving along here. All right, so we could organize our work here where we are going to take a look at, going to a very large and past to infinity the number of compounding periods per year. The short answer is that when you pass to infinity the number of compounded per year, you end up with an exponential expression. Okay. How does that work out? Well, let's take a look above here. Now, this is algebraic manipulation. This is the sort of thing that you do a lot when you're in calculus, especially when it comes time to evaluating limits. All right, so we're going to see what it looks like when you take the limit as n goes to infinity. All right, so we're going to take our compound interest formula, and the first manipulation is by writing r over n as 1 over n over r. And you see the exponent of n. By the way, this is just for 1 year, so that's why you don't see an nt. Now, this exponent of n, what we're going to do is we're going to multiply and divide by r. Now, when you take a number and multiply and divide it by the same number, it doesn't really change anything except the way it's expressed. So now we have nr over r. Now you can then pull out an r as the outer exponent using that power rule for exponents. So now you can write your expression like this. And now treating n over r as kind of an unknown quantity or a variable unto itself, you can make a little substitution. Call it h. So wherever you see n over r, replace it by h. And then you have this expression right here. So we had n over r right there. And we plugged in h there. And we had n over r there. And we plugged in h there. Now, the larger that n becomes, the larger that h becomes. R is going to be fixed. So when n becomes infinite in size, that means h is going to become infinite in size. Excuse me. And by the way, it's going to turn out that 1 plus 1 over h raised to the h power is going to actually become e when h becomes large, when h goes to infinity. And I don't know if Lacey explained that as one way of telling you what e is. E is just the result of taking the limit of this expression here. So you end up with p times e to the r power okay. All right, moving along here. Now, if you have t years that have passed, then that'll go in with the exponent. And this basically says if you have continuous compounding in which you have an infinite number of compounding periods per year, then this right here is your formula. Where P, of course, is the principal, R is the annual percentage rate, and T is the number of years that have passed. Notice that you don't have N in there anymore because N is infinite from the compound interest formula. So now you only have 4 unknowns in this formula here. You don't. Well, you have this equation relating the future balance A, P is the initial balance or the principal, R is the APR, and T is the time. So if you know any 3 of those 4, then you can solve for the 4th by doing some algebra. All right, let's use this to solve this problem then. Find the amount A that results from investing a principal P of $2,000 at an APR of 8%, compounded continuously for a time of 1 year. All right, this is going to be a straightforward calculation. The fact that we're told that we have continuous compounding tells us to use the exponential. We're told that we have a principal of 2,000, interest rate of 8% or 0.08. The time is going to be 1 year. So now we can go ahead and plug in those numbers for P, R, and T. So now you have 2,000 times e to the 0.08. Pull out your calculator and see if you can evaluate this. So tell me what this is. You don't have a calculator? What'd you do for your tests?
I have a calculator I share with somebody.
Okay. Got it. So you know how to use it to do all this. Okay. So 2,000 times e to the 0.08. See what you get. And you should get $2,166.57. You're going to want to round your answer to the nearest cent. Did you get that? Okay. This actually is a pretty easy calculation to do, And even if this were a problem that told you that you were using monthly compounding instead of continuous compounding, your answer right here is not all that different than what you would have for monthly compounding. It would just be a little bit more. So it would be reasonable to expect to have your ending balance to be about $2,166, a little bit more if you had monthly compounding. This is always going to be a little bit more. The result from using the continuous compound is always going to be a little bit more than any ending balance when you have a finite number of compounding periods. But at least it gives you a decent approximation if you have monthly or more compounding periods. Okay. All right, moving along here. Now, let's talk real quick about effective rates. Same thing as yield. You hear the term annual percentage yield, or APY. That's the same thing as calculating the effective rate. Or in other words, the return on your investment, or the rate of return. All right. So, just as a reminder, you probably know this, but I'm going to remind you anyway. When you want to calculate the relative increase in the value of something, basically you take a look at the new value and you subtract off the old value and you divide by the old value, right? Remember that back from previous class? Whatever. That's just going to give you your relative rate of increase for that, whether it's an account balance or the value of an investment or the age of something, I don't know. Whenever you have a numerical value attached to something. So this is how you do it. So suppose that you invest $1 into your bank account on January 1st at a certain APR. Now that $1 would be the original or the old value. The new value is going to be gotten by taking a look at that balance after that dollar has been in your bank account for 1 year on December 31st. And, of course, that'll be, you're the $1 times 1 plus R over N raised to the N times 1 power. Of course, so it's basically the compound interest formula for 1 year for $1 principal minus the $1. And of course, when you divide out by $1, that actually divides out the units of dollars. And you'll just be left with the decimal, which you can write as a percent. And that'll give you your effective yield. Okay? All right, so I'm going to actually erase this ink and I'll show you the solution here. All right, so for this problem, we had $1,000 as the principal, 3% APR, compounded monthly, so N equals 12. So that $1 or 1,000, it doesn't really matter what it is. In this case, it's 1,000. This is going to be the balance at the end of 1 year. Using the compound interest formula. So your absolute increase is $30.42. But the relative increases would be where you take this 1,030.42, subtract the original, which is the 1,000, so you get 30.42, and then divide by the 1,000. And then you end up with, if you take that $30.42 increase divided by the 1,000 original value, of course the dollar signs cancel, and you basically will have 30.42 divided by 1,000. And what does that get you? That gets you 0.03042. Just a decimal, right? But convert this to a percent, and that's 3.042%. Now, hold on just a minute. Didn't you say that the APR was 3%? So shouldn't this, investment vehicle be giving you a rate of return of 3% per year? And the answer is no. This is how you calculate your annual rate of increase of your balance. It's increasing at 3.042% per year. What the 3% APR refers to is kind of like a reference. That is the percent that it gets sliced by the number of compounding periods per year. In this case, 12. It's kind of like the base/reference percentage rate. Not the same thing as the yield or the rate of return. So this is an example. Now, I would always suggest to make it even more simple than this. I don't really care whether you invest $1,000 or $1. The calculation really works out the same. So I always like to tell people, just instead of any other balance, just treat it as $1. Let me erase this ink here. So you have $1 at 3% monthly compounding. So after 1 year, that $1 became this right here. That's the new value of the balance, minus the original $1 that you had invested, divided by the original $1 that you invested. That you're calculating the relative rate of change of that account balance where you invested that dollar. But it turns out, of course, when you divide by that $1, the dollar units cancel, and you just are simply doing 1 plus 0.03 over 12 raised to the 12th power minus 1. Let me pull out my calculator. Let's do that calculation on the calculator. So in parentheses, we have 1 plus 0.03 divided by 12, close parentheses, raise that to the 12th power, and then minus 1. And there's your 0.0342, approximately. Okay. All right, can I go forward? All right, moving along here. That's the effective rate of interest. It's the equivalent annual simple rate of interest that would yield the same amount as compounding after 1 year. In other words, if I were to have invested this $1,000, and instead of doing any compound interest, just paid you 3.042%, then at the end of 1 year, I would have the same balance as if I were to have compound interest at 3% with monthly compound. Okay? Does that make sense? Everybody understand? what yield means or effective rate? Okay. If you have any questions about anything, please let me know. You want me to stop or anything? So here's the calculation. I just kind of showed you on the previous slide, but you invest that $1 for 1 year and then subtract it out again. Except leave off the dollar signs. Or if you have continuous compound and then you have e to the r power and then minus 1. Because e to the r would be what calculates your balance, for investing $1 for 1 year at an interest rate r. Okay. The notation R sub E, that little subscript E, of course, means effective, as in the effective interest rate. Again, R sub E stands for the annual percentage yield. Same thing. I don't know if there's any banks that today do it, but it used to be that you could walk into a bank 20 plus years ago, and this is before everything was computerized, and every day they would have the little signs with the little white plastic letters and those little signboards with the horizontal black felt sort of things. You know what I'm talking about? Those, the letters are always falling out and stuff, and they would always update those every morning with the new interest rates and stuff. They would, for a lot of their loans and investment vehicles, they would have a column for rate, and the second column was the yield. It's exactly what we're talking about here. And if you were to go to any bank's website now, they may or may not be telling you what the yield is, but now you know how to calculate the yield if you know what the interest rate is. Okay. All right, so now we're going to compare banks here. Suppose that you want to open a money market account. I was about to call it a monkey market account. A money market account. You visit 3 banks to determine their money market rates. Bank A offers you 4% APR compounded daily. That's pretty good, right? Compounded daily, 4%. Bank B offers you 4.1% compounded monthly. And Bank C offers 3.95% compounded continuously. So, if the interest rate was all the same, then you would get the better deal with the bank that has the continuous compounding, right? But that's not the same. That's not what we have here. We have different interest rates and different, number of compounding periods per year. So, which one do you have the best deal with? Which gives the best return on your investment? So we could go ahead and calculate our effective rate for each case. So Bank A, where we have 4% APR with daily compounding, there's the calculation for the effective rate. And that works out to be about 0.040884. Okay, not too bad. But we need to compare that against the effective rates for the other 2 banks. So Bank B, they have monthly compounding with an APR of 4.1%. So there's the calculation for their effective rate. And that works out to be about 4.178%. So it looks like we're going to get a better deal with Bank B. But Bank C, they are offering a smaller interest rate, but it has compound interest. So is that going to give us a better effective rate? Well, that calculation for the effective rate for compound interest is actually pretty simple. Four, keystrokes on your calculator. So you take e raised to the 0.0395 minus 1. And that works out to be about 4.029%. So which of these effective rates is the highest? This one, huh? So that's how you can compare which bank has the best rate of return for your money. So you've got this chunk of money, maybe you got an inheritance from your Uncle Charlie or something, or a big tax return, and you don't want to go out and blow it. You need to invest and save it for down payment on a house or something 5 or 10 years down the road. So which bank are you going to go with? Maybe probably Bank B, huh? Of course, you have to look at other things like fees and, how secure your investment is going to be there. So there are other factors that go into it. But at least you know how to calculate which one gives you the best rate. Okay. The best yield, the best return on your investment. Huh. All right. Now, for any investment, its value is going to change with time, huh? Whether we buy an antique car or you buy an ounce of gold or a share of stock or a bond, whatever it is, its value is going to change. And if we're investing our money into it, we would certainly hope that its value increases with time. Now, for this calculation that we're going to do, we have invested money into a savings account, and its value is increasing with time. And we know what a compound interest formula is, that A is equal to P times 1 plus R over N raised to the NT. Now, present value problem refers to, suppose that I know how much money I want in the future. How much money do I need to invest now in order to get that future balance? If I know the interest rate and how much time is going to pass and the number of compounding periods per year. Well, what you could do is you could take this equation. You're going to know what A is, but you don't know what P is, so you can divide both sides by this stuff right here, so you can solve for P. So you're going to have P is equal to A divided by quantity 1 plus R over N raised to the NT power. But that's a little bit clumsy, isn't it? But we could use negative exponents by saying that this is A times 1 plus R over N raised to the negative NT power. So you tell me what the future balance A is going to be, the interest rate R, the number of compounding periods N, and T is going to be the number of years past. And then I can calculate the present value, aka the amount of money that I need to invest as principal now in order to get that future value, A. Okay? So that's what the problem. So we're going to know what A is. We're going to know R, N, and T. And solve for P. Okay? So when you see this formula, I had derived it for you. if you have continuous compounding, remember that A is equal to P times e to the RT. So if you want to solve for P, then you could divide both sides by e to the RT. So that you've got P is equal to A times e to the negative RT with the negative exponent. That's only if you have compound interest. Continuous interest. Continuously compounded interest. Okay. Does anybody need a break? Okay. All right, so I got a question for you. Now, we have what we call a zero coupon bond. Bond is nothing more than just an IOU where a company / corporation / maybe a local government entity, maybe it's a school district or a county or federal government, has issued you a bond and you've lent them some money. That's really what a bond is. IOU. Now, zero coupon means that they're not going to pay you any interest. Now, a zero coupon bond can be redeemed in 10 years for $1,000. How much should you be willing to pay for it now if you want a return of 7% compounded monthly? Or 6% compounded continuously? Now, you need to make sure that you know what the future amount A is, what the rate of return is, or the interest rate is, R. N is going to be the number of compounding periods per year, and T is the number of years that pass. Do we know all that information in the statement of the problem? Yes, we do, because we have a time period of 10 years, that's T. The value is $1,000. We're going to use that as our future value. 7% or 0.07, that's going to be our interest rate for part A of this problem. And then compound it monthly, that means N equals 12. So put all that stuff together and let's answer part A of this problem using the present value All right, so plugged in all those numbers. Now on your calculators, go ahead and plug this expression in and verify that you actually get this number, $497.60. Go ahead and plug that in. Just verify it. So I'm going to pull out my calculator too. We have 1,000 times 1 plus 0.07 divided by 12 raised to the, and then we're going to have, what, 12 times 10, huh? 120 months, huh? Oh, that exponent's supposed to be negative, isn't it? Huh? So I'm going to go back in here and make sure I put a negative in front of my exponent. I'm going to do an insert, a negative sign. There we go. There we go. $497.60. You may want me to show you the calculation again? Okay. So if I want to have a dollar value of $1,000 in 10 years, with 7% APR monthly compounding means that I would need to invest $497.60 today. Okay. With Part B, where we have continuous compounding, we'll just have the more simple formula for the present value, where we plug in 1,000 for A and 0.06 for the interest rate R and 10 for T. And I'm going to pull up my calculator here. So we have 1,000 times E raised to the negative 0.06 times 10. And if we did it right, we had $548.81. All right, any questions on these calculations? No? Okay. All right, now we're going to determine the rate of interest or time required to double or triple or however, any multiple that you want of your original investment. So suppose that we invest $1,000 into our savings plan. How long does it take to become $2,000 or $3,000, whatever? Well, I'll show you the general idea here. Is we're in the form of an example here. What annual rate of interest compounded quarterly should you seek if you want to double your investment in 6 years? We could just as well ask the question of how long does it take? How much time would be required? But the point is that instead of, telling you what A is and solve for P, or tell you what P is and solve for A, this time you know what A is and you know what P is, then you need to either solve for N, R, or T. Okay. So for these doubling problems, your future value A is going to be twice whatever P is. But you're going to have to use some algebra skills or your graphing calculator to solve for R or N or T for these problems. Now, for this problem, they want you to tell me what R is. Tell you to calculate R, which will do the doubling. If you know what N is quarterly, so 4, and T is going to be 6. And if we want to talk about doubling, that means that A is going to be 2P, as in twice the original principal. So if A is going to be twice the original amount, twice the principal, you can replace A by P. So this is kind of what's going to look like. Then the P's are going to cancel. And then, hey, we've already had a discussion of solving exponential equations, right? So we could use logarithms to solve for R, as we shall see. I'm going to erase this and go forward with the solution. All right, so replace A by twice P, because after all, it doesn't really matter what P is. We just want to know how long does it take for whatever that principal is to double in value. And then replace N by 4, because it's quarterly compounding. And replace T by 6, because 6 years have passed. So you have an exponent of 24. So now you have this equation right here. How do you solve for r? Well, I would suggest, I don't know, either taking a logarithm of both sides or taking, raising both sides to the negative 24th power, one or the other. So in this case, you can, actually to the 124th power. Sorry, raise each side to the 124th power. You can get it to it either way. You can use logarithms or powers. So you could to raise each side to the 124th power. Of course, the 124th power means the 24th root. So that's what you see right there. And of course, that's something your calculator can easily evaluate. And then you could subtract 1 and multiply by 4 to get r. So, and folks, this is just a number. That works out to be about 0.1172 or so, about 11.7%. Now, how would you do this if you want to use logarithms? Actually, let me erase all the ink. So I'm going to actually back this up a little bit. Solve this equation for r using logarithms. Well, you could take natural log of both sides here. Natural log of 2 is equal to natural log of 1 plus r over 4 raised to the 24th power, which, by the way, that exponent 24 can come down. So you're 24 times natural log of 1 plus r over 4. And then what? Now, as you stare at this, we've got a problem, don't we? Because it's r that we're actually trying to solve for, isn't it? So I was wrong when I said we could use logarithms. We could use logarithms if we want to solve for the exponent t, but not here. So I apologize. So we can't. Do you see why we can't solve for r here using logarithms? Because let's just go forward a little bit more. If you have natural log of 2 is equal to 24 times natural log of 1 plus r to the 4th power. Well, let's see. Let's see what happens. So that means natural log of 2 over 24 is equal to natural log of 1 plus r to the... Actually, maybe we can. Because what happens if we were to exponentiate both sides? Then we would have e to the natural log of 2 over 24 is equal to 1 plus r over 4. So actually, this might work out. Hey, this is pretty cool. So that means that r would be equal to 4 times e to the natural log of 2 over 24 minus 1. Is that the same thing? Plug it in your calculator, see if it is. This is an exponent, by the way. That's what I'm going to do. I always like to try new stuff. So pull out my calculator here. Help me out in case I forget something. So I'm going to do 4 times exponential, and in parentheses, I'm going to do, what was that? Natural log of 2. Divided by 24, is that right? Get out of the exponent there, minus 1, is that right? Drum roll. Hey, gave us the same answer, didn't it? So we could use logarithms if we wanted to. That's 11.72089. And that's a percentage. I could write that 11.7%. So yeah, you could use logarithms. It's just a little bit messy using logarithms. So you could use powers or logarithms to solve that equation for R. Hey, I'm all for finding multiple ways of solving your problem, so that's cool. So I'm going to erase this ink right here. And if you didn't quite catch it, then watch the video. And then you get the same thing. Yep. So, the conclusion of this problem is that we found the interest rate approximately 11.7%, such that if you were to invest some money, P dollars, that 6 years with quarterly compounding, that if you have interest rate 11.7%, you'll double your money in 6 years. Okay. And you can use the same sort of process if you need to solve for T or N. All right. Now here where I'm actually going to give you this problem and give you a couple minutes to work on it, and then we'll take a look at the solution together. Now suppose that we have some investment, and instead of doubling, we want to find out how long it's going to take to triple it. Now we could start off by doing the doubling problem, find out how long it's going to double, but then redo the problem to see how long it's going to triple, how long it's going to take for it to triple. So what information are we given? We're given that we have interest rate of 6% and that it's compounded continuously. Well, so we don't need to know the value for n. In fact, you could use this little formula down here. So answer part A and part B. How long does it take to double and how long does it take to triple? And I'm going to pause my recording. We'll go ahead and take a look at the solution. Now, before we plug in any numbers, let me just start off with this formula. A is equal to P times e to the RT. And if we want to solve for T, then we could do a little bit of algebra here. We could divide both sides by P. And then take natural log of both sides. And then divide both sides by R. So you have T is equal to 1 over R times natural log of A over P. And now you could plug in your 6% for R, natural log, and it's a doubling problem, so A is going to be twice P. So A over P is just really going to be 2. So you have natural log of 2 divided by 0.06. That's what the answer is really going to turn out to be. And by the way, for part B, what do you suppose that A over P is going to be for the tripling problem? Well, instead of natural log of 2, it'll be a natural log of 3. Right. So I'm going to erase this ink and I'll put up the answers. Now for part A, shouldn't be any surprises there. Natural log of 2 over 0.06, about 11.5 years. So if you invest $1, $1 million, however many dollars it is, into some investment, whether it's antique car, antique coin, postage stamp, anything of value, including a regular old savings account. And you can count on 6% continuous compounding. How long will it take for your value to double? Well, about 11.5%, 11.55 years. I mean, not percent, but years. And then for the tripling, part B, so you replace A by 3P, cancel the P's, take natural log of both sides, like you did for part A, and then you have natural log of 3 over 0.06, about 18.31 years. Now, it took 11.55 years to double, but only 18.31 years to triple. And the time it takes to going from doubling to tripling will be longer than it goes from tripling to quadrupling, because of the fact that more and more money gets compounded into the balance. To go from one multiple to the next, it's going to take less time, because you're because of the money that gets rolled into it. Okay, so anyway, any questions on these example here for doubling and tripling? We could have just as well asked a question regarding a number of compounding periods per year or interest rate as well. So anyway, that's it for today. Any questions about what we've talked about? Okay. So I will render both these videos, upload them to YouTube, and then I will email the links to these lectures to your DMAC email accounts later tonight. So have a good night.